morning, fancy meat computers. How's everybody today? I hope you're doing okie dokie. I told some of my computer science friends that we're starting assembly, and they told me, welcome to hell. I'm coming to this topic scared. Good! Proper appreciation of the subject is always must be accompanied with terror. Because this is like... So this is the thing about assembly, right? We are talking about the technology that bootstrapped us into the modern computer age, right? This is a good way to sort of view the history of computing in general, right? You have machines which you use to create better and better machines over time, but the old technologies get superseded by new technologies, but they never quite go away. Will I be holding office hours in person today? I will be holding office hours in person today. I will be holding my office hours at the usual stated time from 1:30 in the afternoon to 3:30 in the afternoon. If you want to show up a little bit earlier than that, then I will be there, but it's your problem if you mind talking to me while I'm having my lunch. But yeah. And maybe that's a problem for some people. It hasn't been a problem for people before. Anyway, so. Yeah, assembly programming is terrible. I posted a meme about it not recently, but ever since I've been, just completely destroying the YouTube feed, the YouTube community feed with memes. Y'all have been paying attention to that, and if you haven't, you should subscribe. But there was a meme that I had about assembly programming relatively early on in the gigantic meme dump that is my life. Where is it? Oh, I think I've got two, actually. This one's not actually about assembly programming. But, the truth that you guys are going to find out, which I alluded to earlier on, is that FPGA programming is even lower level than assembly programming. And Verilog is a FPGA programming language. Let me see if I can find. Wow, that is a crusty JPEG. Nice. Let's see here. Gotta load them posts. Load them posts. Down page is more effective. Bop 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 a deep bop doop. There we are. This is not my meme. I steal a lot of memes, but I think that's kind of the point. That's kind of the point of memes, is that you steal them. My friends are doing Verilog in ECE. Yeah, and is it Dr. Nicolici that's teaching them? I took... fun story. When I was kind of a more fresh grad student and still doing courses and junk like that, I did a course in FPGA programming that was like Dr. Nicolici teaches a FPGA programming course at the undergraduate level, and then the grad level is that plus two projects instead of one. And at the time, it was a JPEG encoder/decoder. You just do the circuitry to encode/decode JPEGs. JPEGs. It's not all of the JPEG, not everything in JPEG, but most of the JPEG format. But anyway, yeah, that was a fun summer because I spent literally the entirety, I spent 2 solid months in a basement lab in the annex wing of ITB. Literally, I spent 2 months in that basement lab. That was the first all-nighter that I ever pulled in my life, and it was I barely got working the thing I was supposed to get working, and it was good God. Well, I found out that they don't actually pipe air into those rooms on the weekends. So that was kind of fun. It was like, am I getting sleepy or am I like suffering oxygen deprivation here? And it was like, yes. I really don't see any good reason why the windows shouldn't open in rooms. And I know that it's like a basement room, so it doesn't have windows anyways, but like, why are all the windows shut? You know? It's like they can't trust us with windows. It's very insulting. Anyway. Are we going to be tested on this assembly stuff? Oh yes, my friend. There are a couple of questions on assignment 5 that you'll be tested on assembly, and there is going to be a assembly question on the exam. This is material that has been mandated that we cover by the Accreditation Bureau. So yeah, this is not optional material. You'll still pass the course if you do no assembly programming whatsoever and skip this entire unit. I won't be responsible for the outcome on your grade, but you will be able to still pass the course. However, I actually have to do separate learning outcome measurements for each of the different types of things that we cover in the course. So I have to break the grades down and report back to the Accreditation Bureau how specifically you guys did specifically on assembly programming. So I hope that you take this stuff seriously. It reflects poorly on the course and my own teaching if you all learn all the good stuff but none of the hard stuff. Will it be very explicit that the question is meant to be done in C or assembly? Yes. Yes, it's yeah. Yeah. Normally what I do, what I did on the exam last year is I did a subsection. It's this is the assembly this is the assembly component. This is assembly programming, this is C programming. This will be clearly delineated. And besides, you'll be able to get the flavor of what an assembly question looks like, because it's oh, I could do this in C in 3 lines. You know? Oh, he's having me do one while loop and an if statement. And it's worth 16 marks. Big think. What language is this supposed to be in? Yo, I know you said that question 3 on this assignment is a toughie, but personally I found it super, super fun. Ah! Awesome! Is it possible that we could get more open-ended questions like that on assignment 5 plus the exam? Yeah, I mean, one of the things that I was, in my courses, I always for the exam questions, one of the things I like to do is I like to give you a game to program. In my Python course, I've done program me checkers, program me Go. We a simplified version of Go with very simplified very simplified rules with respect to scoring. The scoring in Go is the most complicated part algorithmically, aside from capture detection. But never ask the prof for more homework. Yeah. I haven't even been able to finish any of the questions for A4 so far. Well, finish a simpler version and then try to get a more complicated version online. Oh, it's a printf statement. Approximately 500 lines. Yeah, that's your choice. You can use the tools available to you or write an ungodly amount of if statements. Anyway, so we were talking about intro to assembly programming. So let's continue with that. I don't think it's more, but if other people do, I will retract my statement. Yeah, don't worry, Avery. Honestly, I I think you would be interested in, like, some coding competition questions. Wow, you thought that the question 3 on assignment 4 took less time than shell sort? That's, like... That's interesting. You might have the makings of a compiler man. You might be, you might have a well-suited brain to programming compilers. Because that's basically the point of this question, right? This parsing question. I used to do coding competitions in high school. Yeah, the coding competitions are great. So, like, that's kind of the point. That, so to speak, the point of the question is, like, this is like approximate to the manner in which a computer programming language is fed into a computer itself and then turned into instructions, right? You can do question 3 without pointers. Yeah, you can definitely do question 3 without pointers. I have set aside the weekend for just question 3. How screwed am I? I mean, I think you'll be fine. Like, 2 days is plenty of time. To be honest with you, I think the right time for you, for anyone, for that question, which is reasonable, I think, like, I don't know, if you're spending more than 4 hours on it, you're using too many, you're probably thinking too hard about it. Like, that's the problem a lot of people have with programming, is that they think too hard about it. You know? The whole point is learn how to compose the simple operations, right? It's like, don't think in terms of the complicated operations. Think in terms of many small, simple operations, right? But anyway, because that's how the computer thinks. And to program, you have to think like a computer. But anyway, speaking of a series of very simple operations, let's talk about assembly programming. So we were talking about how assembly programming is essentially programming in the native language of the CPU itself. So every CPU will have an instruction set architecture, or ISA. These are often relatively stable in, like, a series of CPUs, so you don't have to worry about, like, every version of an Intel chip having a different ISA. Typically, the ISA will remain constant while they'll perform upgrades on the CPU itself. But the ISA dictates what operations the CPU can perform on its data. So, different processing architecture, different ISA, different commands available, different assembly language for each CPU, essentially. So, let's talk RISC versus CISC. So, instruction sets are generally placed in 2 categories. You've got CISC machines and you've got RISC machines. CISC stands for Complex Instruction Set Computer, and RISC stands for Reduced Instruction Set Computer. CISC CPUs tend to be the older, more well-established proprietary ISAs, such as Intel. A large set of instructions means these CPUs are highly complex and expensive. They're typical for desktop, supercomputer, or other high-horsepower applications. So, you know, your laptop/desktop computer is going to most likely be running a CISC architecture with an Intel chip, right? There's kind of a trade-off, right? For every instruction that you implement in a CPU, you are actually having to put circuits into the computer, into the chip that actually perform that operation, right? So the more instructions you support, the larger your chip becomes. But basically the problem that companies like Intel run into, like in the year 2021, is they kind of have to maintain back compatibility. Like, it's very similar to how the language C works, how it has had language expansions over time. It's like you want old programs to be able to run on the new CPUs, right? So you have to maintain as the like if you imagine like an older version and a newer version of a CPU both having their own instruction set, the instruction set of the newer one has to be a superset of the instruction set for the older one. That is to say, you can only add instructions, because if you start removing instructions, you start running into immediate back compatibility issues. It's kind of like the old Game Boy Color cartridges. A lot of them would be playable on an old Game Boy, but in black and white. That's because to go from like a standard Game Boy to a standard Game Boy Color, the Game Boy Color's instruction set was like still compatible with the old Game Boy's instruction set, which is why like you can get so far on that, but once you hit like Game Boy Advance and especially DS territory, like the DS, I'm pretty sure is running a GBA emulator under the hood. It's not natively supporting GBA in hardware. At least I don't think it would be. They did. I do remember they came out with the Game Boy Micro, which was like a Game Boy that was roughly the size of the cartridge, but which didn't sell very well. But so maybe they did manage to miniaturize it to the point where they could fit it inside the DS. But anyway, so reduced instruction set computers are actually very, very, very popular because that's essentially smartphone architecture. The mass deployment of smartphones, many of which run on ARM, has established RISC processors. They're as well established now as complex instruction set architectures. The smaller set of instructions means more functionalities left to software, but with the benefit of a far less complex processor. Typically, in mobile and embedded systems, where an expensive processor would be overkill, you go for a reduced instruction set architecture. So this is what happens. This is like the life cycle of an instruction set, right? It starts off, it has very few instructions. As it becomes popular and grows, the instruction sets grow as well. The processor becomes more and more and more complicated, right? As it grows in complexity and expense, it opens up a space in the market for a less complicated processor. So some new company, like ARM, comes in and says, hey, we've got this new processor that's like half the price. It's got a reduced instruction set, but like maybe it's like actually like 1/10 the price or something. And it takes like 1/10 the power. And so a bunch of like manufacturers of hardware devices are like, well, yeah, obviously we don't need an Intel CPU for this application. So that the lower price point causes the new architecture to gain in popularity. As it gains in popularity, people request more and more instructions in the instruction set. It grows over time, and that space in the market for a low-cost, low-instruction set CPU opens up again. So this has happened a few times now. Intel, like back in the 80s, this is like Intel's growth from the 80s through to the present day is described by this. ARM's growth actually is described by this starting in like, I don't know, I think ARM started in like the sort of late noughties to really gain popularity. It was probably invented substantially before that, and then it has increased in size as it has aged, and now we have some newcomers in the field like RISC-V, which is actually an open source standard. So you sort of have this interesting thing with RISC-V where a bunch of because like the design of the CPU or the specification of the CPU is open, anybody can view it. Anybody can manufacture a RISC-V processor. So right now there's like a huge market competition going on right now to see who can make the best and most efficient RISC-V processor. So you have various manufacturers, but it doesn't matter that you have various manufacturers because they're all following the same standard. It used to be the only way that you could assure the only way that you could assure consistency in the product is to have one manufacturer of it, right? It's like nobody else makes Intel chips except Intel. But now, a RISC-V chip can be made by like 10 companies across the whole world, or 100 companies across the whole world, you know? But anyway, and a lot of the prototyping for this they're doing on FPGAs, because that's what FPGAs are for, to a certain extent. In a production electronics setting, what an FPGA is it's a rapid prototyping test bench. You would do your design out on an FPGA, and then when you're doing your manufacturing run, you do it as like a regular ASIC, right? I just threw a lot of electronics at you. You might get the impression that this is a subject on which I'm slightly knowledgeable. So, here are some instruction sets. So x86-64 is the instruction set for 64-bit AMD and Intel processors. So x86 is like the general term. We don't really say -64 because it's assumed at this point that pretty much everybody's on a 64-bit architecture. So x86 is used in laptops, servers, other high-end computers, as you might expect. ARM stands for Advanced RISC Machine. It's common among smartphone and tablet devices. So the ARM is like in the middle of the market right now. It's like, obviously your cell phone isn't as powerful as my gaming laptop, right? Or your gaming laptop, or whoever's gaming laptop. But, you know, smartphones are still quite powerful, like, compared to a lot of the electronics out there. Like, they really have evolved into, like, a good general-purpose computing machine, right? If only, like, if they could just solve the problem of having ergonomic inputs and outputs, like that, the smartphone would be like much more dominant in the space. Like, you can get these tiny little boxes, right? That have, it's basically just like a 4-inch cube, a 4-inch on a side cube with like a bunch of like plugs in the back that you can plug like a monitor and a keyboard and a mouse into, and a power supply. And it's basically a smartphone architecture, but it expands the I/O to the point where it can pretend that it's a real computer. But yeah. So, and then you've got RISC-V. RISC-V is an up-and-coming open-source ISA. So far, most RISC-V use cases have been in embedded systems and hardware peripherals. RISC-V is still quite recent at time of writing, so it's probable that it hasn't found its niche yet. Just as the C standard has a number of implementations, ISAs can have a number of assembler implementations, which all implement the same ISA to varying degrees. So, I think I may have already stepped on my slides a little bit. Yeah, I've already said all of this. I'll run through it quickly. To understand the differences between the ISAs on the previous slide, it is important to understand how they came about. In a lot of ways, the development of an ISA is similar to the development of a programming language. One might say that it is a programming language, in fact. While an ISA may start small, over time things tend to get added to it as the designers watch how the ISA is used. This is the same as how long and short integers were added to C eventually. Once an inclusion has been made, that inclusion tends to be permanent, as removing a feature or instruction always runs the risk of invalidating the existing code base. The result is that over time the ISA grows more and more complex, making the CPU larger and more expensive over time, though the added features do represent some degree of improvement. At a certain point, an ISA begins pricing itself out of the market with respect to certain applications, i.e. the processor in your laptop wouldn't even fit in a kitchen timer, let alone, justify the power requirement and the expense. This allows a competing ISA, which meets the needs of an abandoned market, to gain adoption. As this new ISA gains users, there is an increasing pressure to include additional features and instructions, which drives up the cost, and the cycle continues. It's possible. It's possible with ISAs. What am I saying? Yeah, so another thing to keep in mind about smaller architectures, right? They use less power, right? The amount of power that you use is proportional to the amount of circuit that you're powering. So the less circuit you're powering, the less power you use, very, straightforwardly. The other thing to keep in mind about minimizing your instruction set is that you can actually, in some cases, clock your CPU faster, because one of the things that limits how quickly you can clock your CPU is what's called propagation delay, which is the amount of time it takes voltage to propagate through the circuits. More circuits, more propagation delay, so you can't clock it as quickly. Now, that being said, like Intel is very, very good at making chips, right? So, they'll have also Intel chips will be subject to a degree of optimization. Like, an Intel chip has, 50 years of optimization, 60 years of optimization behind it, right? Whereas, RISC-V doesn't, might have, 5 or 10 years of optimization behind it. But, different chips for different applications. Everything's an engineering trade-off. So, let's talk basics. So, this should be a scary, scary sentence for you. In order to program in assembly, you have to unlearn pretty much everything you know from C and Python and any other programming language you know. It is correct to chop this off, think of it in a completely different category than every other programming language you know. Like, when we are programming in C, for example, we are used to having certain things available to us. Statements. Like assignment, right? Assignment is an operation that you don't get for free in assembly. Flow control, or a control flow, like if statements and while loops. There are no if statements and there are no while loops in assembly. You can't declare functions. Well, maybe you can, but at our level, we're not going to be declaring functions. There are a lot of things that you don't have available to you. Although, unfortunately for you guys, pointers managed to make the transition. So, in assembly, each statement is a single CPU instruction. It is an instruction on one of the registers in the CPU, one, two, or multiple of the registers in the CPU. There are no assignment statements, there are no if statements, there are no while loops. If I can't even assign things in assembly, what am I supposed to do? Well, that's what we're going to see. The short answer is you can do it, you just have to do it manually. Even things like functions and symbolic variables are very different in an assembly environment. Yeah, like variables don't really exist either. You have registers. And in order for a register to mean something, you have to remember that it means something. About the only concept that isn't radically different is pointers. Yeah. So, here's your assembly programming survival kit. In this course, we are going to learn the rudiments of ARM assembly language. It is highly probable that you will be trying out ARM assembly on a system that does not have an ARM processor. As such, we will need an emulator to be able to write and execute ARM assembly instructions. We will be using the visual assembly emulator. Please download and install the following. HTTPS / this bitbucket thing. Hopefully it's still there. Yeah, there, it's still there. So this guy, a highly visual ARM emulator. Question. So assembly is like speaking to a grammar Nazi with no short-term memory. It's like speaking to a... Okay. It's like speaking to a highly unintelligent grammar Nazi with no short-term memory who will do everything that you ask, regardless of as to whether it makes sense. But that's kind of computing in general, actually. Like, that might be a decent description of computing in general. But anyway, so get this. You're going to need this program to perform the assignments, so download it and install it, please. Visual does not support enough features to be something you would actually use in a practical scenario. It's closer to a debugging IDE, but it'll do for instructional purposes. So, like, the issue that we have is, like, because there are so many different assembly languages. Assembly, please delete System32. Hey, if you can find System32 with assembly, yeah. Yep. Is the emulator compatible with Linux? Yes. If you take a look, it's got releases for Windows, Mac, Ubuntu, 32, and 64-bit. That being said, it hasn't been updated since 2015, so, you know. It'll do. This is like... It's not the best piece of software that's ever existed, but it's it functions for our purposes. Because, like, the purpose here is not to give you enough assembly programming that you would be able to write assembly programs in a practical sense. That would be impossible with the amount of time we have remaining in the course. Can't download, eh? Let's see here. Uh-oh. Uh-oh. Well, if you're on Linux, you can probably get it through Synaptic. Shit. So Ethan says it works for him. No, it doesn't. Oh boy. Well, that's a problem I'm going to have to get fixed today. Wait for your announcement feed. Should you download Visual for your Windows or your Ubuntu Windows subsystem? It's your choice. Looks like we don't have to learn assembly. We do! It's an accreditation requirement! Yeah. Yeah, unfortunately, it's an accreditation requirement, so we can't just skip it, guys. Just because, like, you guys give up way too easily. Friggin' Zoomers giving up way too easily. That's right. I brought generation into this. Shit. This worked last year. Damn it. Alright, well, we'll just continue on with the lecture. Should we wait to try to download, or we should do it right now during the lecture? Well, apparently I have to find a new emulator. But, yeah. Yeah. Are you guys doomers, then? Yeah. Great. I downloaded it at the beginning of the semester, and it worked. Do you have a copy of it? Jack, could you maybe, like, if you have the program, could you maybe, yeah. You know what? This is what we're going to do. We're going to see if we can piece together the executables. We're going to see if we can piece together the executables. I'll put them up on Avenue, and then we don't have to friggin' worry about friggin' this guy on his friggin' website. So, I mean, millennials are the ones who started it. Millennials are, like, way too serious about everything. I personally would not want to live in a world run by millennials. Is there any hope for humanity? There's always... Where there's life, there's hope, man. Where there's life, there's hope. I had a tree in the backyard that, like, I thought I had killed it when I tried to transplant it, but I just kept watering it, and it had, like, 2 leaves, and it is now, like, a perfectly healthy tree. Where there's life, there's hope. So Jack has the Windows version. I'm pretty sure I have the Linux version, and, I don't know, maybe I'll get in contact with, like, the old, like, last year's class, see if any of them have the Mac version. I don't know, Mac people, you might have to emulate it on Windows or Ubuntu or something. Gugh. Are there any Mac users in the crowd? I suppose that's not a useful thing to ask because the entire class isn't here. But, yeah, Jack, shoot me an email. I think I'm gonna have to yoink that executable from you. Mac should have a Windows application emulator, right? Pretty sure. So anyway, we're doing assembly programming without the survival kit. All right. So this is what I would consider Hello World in assembly. Actually interacting with standard output from assembly is pretty complicated. So this is just a very, very simple program. This very, very simple program is a do-while loop that just counts from 0 to 10. Or, what does it do? No, I'm sorry, it sums the values between 10 and 0. Pardon me. So this is what assembly looks like, right? So, this line, int total equals 0, you move 0 into register 0, R0 accumulates the total. Incidentally, in ARM assembly, a semicolon is the beginning of the comment. It's the beginning of a line comment. You then move 10 into R1. You add R0 and R1, place in R0, subtract 1 from R1, place in R1, and then you branch on not equals back up to the tag again. So basically, everything. Assembly is the better program. It only takes 5 lines. Yeah, well, yeah. So variables don't get names. You just have to remember what register you put the data in when you want it later. This is where commenting would come in handy. There's no control flow. Everything is go-to statements. Like, your control flow is go-to statements. Incidentally, the subtract s is like a subtraction operation combined with comparison. Comparison to 0. So, once we get it working, this is what visual is going to look like. So, in the left pane, you write out your program. In the right-hand pane, you can see what the values in each of your registers are. So this really is like more like a debugging IDE than it is a like something that you would actually produce an executable with. Like, as far as I'm aware, there's no way to actually produce an executable with this program. It's like the debugging output is what you're looking for. But yeah, so you sort of run this, and you can step forward, step backward, execute the whole thing. You know, standard sort of set breakpoints, standard debugging stuff. So that's why we're not allowed to use gotos in this course. No, it's why, like, gotos are terrible. Don't ever use them in C, but in assembly programming, you have no choice. So you must use gotos. Gotos are terrible, terrible, terrible practice. It has been well established in the programming community that use of goto statements has been terrible practice since the 70s. So please don't use gotos, except for assembly programming. That being said, gotos are a more general control structure than if statements or while loops, so there are additional control structures that you can create with gotos that are impossible in C programming. And this is one of the reasons that assembly optimization is the highest level of optimization. So, yes. So you can execute this stuff. You know, that says emulation complete. So you can see, click on a line number to restore the program to that state at that number. So you can actually like pull down a drop down for each of these registers and view how they change over time, right? So this is the view for R0. You can see it starts at 0, then we add 10, then we add 9, 8, 7, 6, 5, etc., etc., as the program progresses. I figured out how to download the link from the website. Tell us! Tell us! How do you download the link? Please don't be pulling my leg. You open it in a new window? Untitled? What is it? Tell me! Use inspect element. Inspect. Uh-huh. Inspect element, and then click the link? Frick! Hallelujah! Oh my gosh! Okay, thank you, Corbin. Corbin just got an A+. He earned it. So what I'm going to do is I'm going to download all of these bastards, and I'm going to put them up on Avenue so we don't have to worry about this again. But thank you so much. You're probably my favorite human being. You're the man of the hour. All right, this is the Mac package. This is the Ubuntu package. This is the other Ubuntu package. There we go. All right, now I'm going to put them right up on Avenue right now. I wonder if the person who put together this emulator realizes that we're using it for a class. Resources. Visual ARM assembler. There's the link. but let's actually. So did I put those in downloads? Let's see here. Visual OS X. Blop. Visual Windows. Oh, it's going to take a while to upload. I should not be doing this while I'm uploading a stream, eh? But, oh well. So we'll get that done. Good. Thank you so much. You guys are my favorite. Favorite class. How do you change the font sign on the emulator? After the trouble we had just getting the bloody thing, you're going to ask me a question like that? I don't know how to change the font size on the emulator. Might be using a system font size. So, let's break this down. Assembly programs are broken down by tab-separated columns. You can think of an assembly program as being like a table. So you've got 5 columns. Sometimes you have more columns than this, but most instructions will have 5 columns. You have a column for labels. You have a column for the instruction code. You have then 3 operand columns. Right? So move is an instruction, add is an instruction, branch not equals is an instruction. Sometimes a label can be an operand, like if it's a branch instruction. So it's like, so what branch not equals does is it says if the result of this is not 0, then go back to the label again. So you go back to the label again, and then you continue the program from like this point. It's really a very straightforward manipulation of the program pointer. Okay, there we go. So OS X is up. Windows. Bing, bang, boom. Instructions and operands. Yes. So, the above example uses 4 different instructions. So we're going to review what these instructions actually do. Move moves the contents of operand 2 into operand 1. So the convention, roughly speaking, for all of these operands is the first operand is the thing the result is getting stored in. So the C equivalent of this is op1 is equal to op2. So this is it's like assignment, but not really, right? So with an assignment, you're storing to a variable that is contained in the stack frame, right? With this, you're just moving data between the registers of the CPU itself. So registers are the inbuilt memory inside of the CPU. So add, op1, op2, op3, computes the arithmetic addition of operands 2 and 3 and stores it in operand 1. The C equivalent is op1 is equal to op2 plus op3. Sub S is a little bit more interesting. This computes arithmetic subtraction of op2 from op3 and stores the result in op1. So computes R1 minus the literal 1, stores it in R1 again. Incidentally, in ARM assembly, if it's got the octothorpe character in front of it, that makes it a literal. The instruction is actually sub plus S, where the S suffix indicates that the instruction also sets the status register. This is necessary for control flow purposes. So I think that I've got just one more. All right, there we go. So the status register is what controls branching, go-to branch executions inside of assembly, right? So the status register is a very special register that keeps track of, for example, like when you call a comparison operation, right? If you compare op1 and op2, it basically performs subtraction and stores the result in the status register. So if you can add and move operators, what are their values? No, you can't. That's operand, not operator. Where it says op, think register. These are operands, not operators. No, the instructions are the operators. These guys are the things being operated on. The technical term for that is an operand. The equivalent code in C for sub is op1 equals op2 minus op3. So that's class, however. So I need to stop talking so that you can have some time for all of this yummy information to filter down into your brains. Are there any further questions? Addition and subtraction is not that difficult to understand in assembly. The thing that gets people about assembly primarily is control flow and memory interaction. So, okay, so if you can add and move operands, what are their values? Whatever is stored in the register at the time, right? So, does space matter? What do you mean by space? Like white space? I don't think white space matters, but generally speaking, like it's hard enough that without messing around with the white space. How does it know when to end the loop, the again loop? Well, we're actually going to talk about that when we talk about like the branch not equals, which we didn't quite get to because class is over. So if you can just hold that question for next week. I apologize I didn't quite get to it because I spent too long waffling about processor architectures, which hopefully was still useful information to you guys, but yeah. The short version is that the branch statement looks at the status register in order to see whether particular bits in it have been set or not. If the subtraction results in the register being 0, then sub S will set the status register differently. Branch not equals looks for that specific difference, and then it'll only go back to again if this guy comes out with a non-zero value for R1. Otherwise, it'll allow control to flow through it. So that's what controls the loop. But that's the short version. Incidentally, ARM assembly is probably the best assembly language I've seen. Like in terms of its syntax, it's the most clear. It's the most clear assembly language I've seen. So, are the contents of op1 overwritten when op2 is moved into it? Yes. Emphatically yes. Absolutely yes. It's basically a set operation, right? It's like set this register to that register's value, or set this register to that literal's value. And a literal in assembly programming is just like a stored sequence of bits that you refer to. Also, any updates on if we'll get the full solutions to past assignment? Next question. What if we write the C code, then use a translator? Can you find an, like, I have cracked the code. I mean, technically speaking, you can actually compile to assembly using GACC. But I don't think that you can, compile specifically to ARM assembly using the standard distribution of GCC, so you might run into some issues. I'm pretty sure that it would only compile it to x86, and the assembly programs that I'm expecting you to write are for ARM assembly, which is more applicable to your embedded systems environments anyways. So, yeah. Technically speaking, I'm pretty sure that the GCC has a mode where you can get it to output an assembly code, like an assembly program, but, you know, it's like, stop this before it becomes object code. It's like, okay, here you go. Because that's the other thing to realize about assembly code, right? Although, like I have said, that the assembly code is the same, it's the same operations that the CPU uses, it's still different from object code, right? Like, an assembly program still has to be compiled in order for it to be readable to the CPU directly, right? It's like, and this is not just a matter of, like, encoding these instructions as, like, binary data instead of as strings. Like, you still have to compile assembly. But I think there actually is one. Converts C to ARM64 GCC 11.2. Yeah, the point is that you learn how to program assembly natively. Something tells me, if you were to actually perform that process, you would get a very long assembly program. And it wouldn't be easy to pick out, like, what exactly, like, where your program, like, these 5 lines of assembly code, it wouldn't be easy to find them inside of the, like, you know, 2,000 or 3,000 lines of assembly code that GCC spits out at you. Dislocated ear cartilage. One of the occupational hazards of living a life where you have headphones on all day. If you're going to wear headphones all day, you should have comfortable headphones. I would rather write it myself as not to shoot myself in the foot. The foot. Yeah, will we be doing more C in this course? Ha! That's an interesting question. Technically speaking, no. Let me give you a review of our upcoming topics. So, after we're finished assembly programming, I've got 2 more topics lined up for you. One on makefiles, and one on profiling, which is like, both of these are topics, like, that are directly related to C programming, but not, like, learning the C language itself. These are, like, auxiliary skills. I would have, like, I kind of, like, I really wanted to, like, put the makefile stuff in earlier in the course, so that you guys could make use of it during the course, but unfortunately, it kind of, like, I already had the version control topic that was sort of inserted awkwardly, and, like, if I were to insert another one awkwardly, it would just make all of the, like, it would displace all of the assignments in time. But, yeah. Is the exam going to be all in assembly, then? No. No, the exam, that would be cruel. That would just be cruel to, like, make the exam based entirely on one thing that you cover in, like, week 10 of the course. I'm not saying other profs don't do that, but I would consider that cruel and unusual. No, the primary, just like the test, most of the marks on the exam will be derived from C programming, except there will be like 1, maybe 2 assembly questions in the exam. Like one medium-sized or 2 small ones. It's sometimes difficult to come up with like a good medium-sized assembly program. Like, there aren't that many very, very short programs that are still, like, make a test question, you know? It's like, there are only so many variants on, like, count from 1 to 10 that you can do, you know? I think last year on the exam I put, there's an interesting algorithm for calculating, did I do least common divisor or greatest common denominator? One of those type of things. How many questions will be on the exam? Next question! I don't know, I haven't written it yet. You can expect it to be a little bit longer than the test, probably. It should cover more than the test, because you should be better at programming than you were when you wrote the test. I will post, I'll post last year's exam, the questions, so that you guys can get some practice in. I know, like, I know one of the problems with this course is, like, or maybe you guys differ. Plot twist, I'm worse at programming now. Ha! You were ruined by assembly in one lecture. I can afford to take the entire 24 hours with no sleep since that's my last exam. That's the spirit! What's the most fun topic in this course, in my opinion? Like, the most fun to teach? Well, strings are a pain in the ass to teach. I hate teaching the string material, because it's like, and this is what this function does, and this is what this function does, and this is what this function does. And it's like, I can feel, even through the medium of television, the energy draining from the class, and it also drains from me through that material. So that's, like, my least favorite. I always like the introductory stuff, you know? Like, I enjoy teaching, like, the first 2 weeks the most, I think. Because it's, like, you're not, like, getting bogged down in the nitty-gritty. You can just sort of I can more freely, like, talk about, like, you know, the character of the material. It's kind of like, I enjoyed the intro section here more than I enjoyed this. But, you know, especially since we ran into that issue of, like, the friggin' download link not even working. But, if I were to, like, put my finger on, like, the most fun I had with any topic... Arrays. I'm gonna say arrays. It's like, before pointers and all of that nastiness, but, like, it's complicated enough that we can still, like, say interesting things, you know? Are you trying to assay what the exam questions are going to be from what I most enjoyed about the course? That's a bad plan, sir. What you should be doing is you should be looking up on the internet to see the accreditation requirements for this course. You should look it up and see what questions I have to ask. Yeah, I really like when you give background history of computing and how it all came together. I know, right? Like, it's very, like, it's a fascinating, it's fascinating to me, like, the history of computing type material. Like, how, like, why did they decide that, like, a short int should exist? That type of stuff, you know? Yeah, like, I find that stuff really interesting. And I also think it's, like, important for you guys to hear that kind of stuff, because, like, one of the purposes of going to university and being taught by professors as opposed to just, like, learning C programming from, like, you know, like Geeks for Geeks or some website, like, one of the things that's, like, important for you to pick up is, like, you need to pick up the culture of your profession, you know? And the history of your profession is a very good, like, the history of your profession tells you the culture of your profession. Like, if you know how Unix and C were interrelated and developed in tandem with each other, and then you know that the philosophy that gave rise to C is the same philosophy that runs Linux. And if you know, like, if you know that philosophy, then you can participate in the culture, right? Like, in order to be like a Linux pro, you have to absorb the Linux philosophy. Right? So, you know. Anyway, I find that kind of stuff, like, really, really, like, that's my favorite stuff to teach. And you can probably tell because, like, I start talking faster and I seem more excited when I'm talking about the history of computing and stuff like that. But, like, those 2 slides in the middle of the string lecture on, like, why short and long integers exist are, like, definitely my favorite slides in that lecture, you know. But yeah. Anyway. So, office hours today. If anybody is interested in dropping by, 1:30 to 3:30 ITB 102. If you're having trouble with question 3, I might be able to take a look at your code and give you some pointers. Ha! Give you some pointers. Ha! We'll see what happens. Assembly. All right. Take her easy, folks.